In the last lecture, we proved that the set of C-infinity maps is dense in the space of CR maps between open subsets of Euclidean spaces. Now we are interested in the global version of such a result, in which open subsets of Euclidean spaces are replaced with arbitrary manifolds. Besides that, we are also going to discuss a related problem. Instead of raising the degree of differentiability of a map, as we did till now, we can actually try to raise the level of the differentiability of manifold. In other words, we are going to consider the following problem. If we have a CR manifold, is it true that this CR manifold is CR diffeomorphic to a C-infinity manifold? The answer is yes, and this is a very useful property because it allows to consider any CR map, any CR manifold as a C-infinity manifold. And we are going to see an application at the end of the lecture. Indeed, in a previous lecture, we proved the Whitney embedding theorem for the compact case. We proved that if we have a CR compact manifold, then it's embedded in R to the 2m plus 1, where a small m is the dimension of the manifold. But there was one case missing. We didn't prove the result for C1 manifolds. Now, using that remark that essentially every manifold is a C-infinity manifold, we are going to be able of completing the proof of the Whitney embedding theorem for the case of compact manifolds. So we approached a map between an open subset of Rn and an open subset of Rn, a CR map, with a C-infinity map. But we want to do likewise for manifolds, not just for open subsets of some Rn. And so we need to use the local result that we just proved with some globalizing techniques, as for instance partitions of unity, to try to globalize the result and to prove an analogous theorem for the case of differentiable maps between differentiable manifolds. In order to globalize, we can use the following theorem that we're not going to prove, the relative approximation theorem. You have R greater or equal than 0, smaller than s, less than s, which is less or equal than infinity, and consider U and B open subsets of Rm and Rn, respectively, and F is indeed a CR map from U to B. Consider a closed subset K of U, an open subset W of U, such that F is CS in a neighborhood of K minus W. Then every neighborhood N of F in the set of CR maps from U to B contains a map which is CS in a neighborhood of K and which is equal to F on U minus W. Okay, and it's not difficult to convince ourselves that this result is going to be very useful in order to globalize the density of C-infinity maps that we just saw for the local setting. Because imagine, for instance, that we have here some map K, and we have over here some small open subset W, right? The hypothesis says that F is a CS map in the neighborhood of K minus W, in particular in the neighborhood of this set over here. And what the relative approximation theorem says is that we can obtain now a map that is going to be CS in a neighborhood of K, and in particular also in a neighborhood of this set, and that is equal to F in all the blue points in U minus W. And as I said, it's not difficult to see that this result is going to be very useful to globalize the local result, the local density result that we obtain. Because in this way, we can actually consider, for instance, a locally finite family of compact sets and small compact sets that are contained in local charts. And little by little, by using this method, we are obtaining CS functions, okay, that are CS functions in the neighborhood of a union of these compact sets. And in this way, you end up obtaining a CS function in the neighborhood, in the union of all these compact sets, so in the whole manifold, okay? We're not going to get into more details. In particular, a result that we obtain as a consequence of the relative approximation theorem is that if M and N are CS manifolds with S less or equal than infinity, then the set of CS maps is dense in the set of CR maps when R is less than S. Of course, it's also true if R is equal to S because these two sets are the same. Okay, so we can approach CR maps with CS maps. And in particular, if the manifolds are C infinity, we can approach CR maps with C infinity maps. All right? Okay, these are the two theorems that we just saw. And now we are going to see the consequences of the density of C infinity maps, for instance, of CS maps, if we are considering CS manifolds. The consequences of this density result for stable properties. So consider here J super K of M and N be one of the following subsets. The K is for the class of differentiability, so we are considering CK maps, and we can consider diffeomorphisms. So in that case, that would be the CK diffeomorphisms between M and N, embeddings, that could be CK embeddings from M to M, closed embeddings, immersions, submersions, or proper maps. And now the theorem is the following. Let M and N be CS manifolds, where S is less or equal than infinity. Then this G super S is dense in G super R in the strong CR topology whenever R is less or equal than S. And in particular, a cool consequence of this theorem is that M and N are CS diffeomorphic if and only if they are CR diffeomorphic. Of course, one of the implications is totally trivial. If they are CS diffeomorphic, then they are CR diffeomorphic because R is less or equal than S. But the other implication is also true because M is CR diffeomorphic to N if and only if the set of diffeomorphisms, of CR diffeomorphisms between M and N is indeed a non-empty set. But since the set of CS diffeomorphisms is a dense subset of the set of CR diffeomorphisms, we get that the set of CR diffeomorphisms is non-empty if and only if the set of CS diffeomorphisms is non-empty. And so this happens if and only if M is CS diffeomorphic sorry, to n. So these properties are equivalent. Okay, nice. Let's prove the theorem by as a corollary of the previous result. Okay, so what we have is that, for instance, if we consider diffeomorphisms, the CS diffeomorphisms from M to N are just the CR diffeomorphisms that are CS, right? And now consider U an open subset of J sub R, okay? Let's notice that this set over here, because of stability, is an open subset of CR. So U is open in CR for the strong topology, right? In particular, the density result implies that U intersection CS is non-empty. Okay, let's put it, let's write it over here. Right, it's non-empty. But this non-empty set is contained, okay, in the intersection of GR, because U is contained in GR and CS. So it's contained in the intersection of GR and CS, which is GS. And so we proved that for any open subset of JR, J super R, okay, there is always in that open set an element in GS. And so because of that, GS is dense in GR, okay? So far, we played an interesting game. For instance, consider that we are working with C-infinity manifolds, just fixed ideas. And the game consisted in giving a CR map and then approximating this map with C-infinity maps, right? So we are smoothing our initial map, and the smoothing is close to the initial map in the CR topology, in the CR strong topology. So, but that's basically the game, is smoothing our differentiable functions or maps to make them of a higher differentiability class. We can try to play an analogous game with manifolds. Indeed, the question is if every CR manifold is CR diffeomorphic to a C-infinity manifold. Or in other words, if you have a CR manifold, if we can give to this manifold a structure of C-infinity manifold that is compatible with the CR structure, right? And the answer is yes, and the techniques are similar to the case of differentiable maps, okay? The techniques that allow us to smooth differentiable maps allow us also to smooth manifolds. Of course, there are some differences, but the ideas are analogous, okay? And this is a result that we are not going to prove now. Something that I think it's interesting to say is that if you have CR manifold, you can consider his unique maximal atlas. For this maximal atlas, the change of coordinates are CR diffeomorphisms. And there is an real question, and it's if there exists a subatlas, okay, in which lambda prime is a subset of lambda, if there exists a subatlas such that the change of coordinates are indeed C-infinity. And the answer is yes, because it is equivalent to say that every CR manifold is CR diffeomorphic to a C-infinity manifold. So we can actually give a structure of C-infinity manifold to every CR manifold. An important remark is that because of this result, we can assume essentially, and in practice, that all manifolds are C-infinity from now on. Because if you have, for instance, a C1 manifold, it is going to be a C1 diffeomorphic to a C-infinity manifold. So the properties of these two C1 manifolds, let's say C1 geometry, are the same, but one of them is also a C-infinity manifold, so it's easier to work with that one, right? And as a consequence, we are going to see again the Whitney embedding theorem. We just, we already proved this result, but notice that here we have R greater or equal than 1. In our original proof, we were forced to consider as a hypothesis that R is greater or equal than 2 because of the lack of differentiability that is associated to consider the tangent space. Okay, essentially that was the reason. For R equal 1, we were not able of applying SAR theorem. But let's see that the result is also true for R equal 1. So, okay, consider now that M is a C1 compact manifold, and this manifold is C1 diffeomorphic to a C-infinity manifold. Sorry. So there exists a C-infinity manifold, and that is C1 diffeomorphic to M. So there exists also a C1 diffeomorphism between M and N. Right. Now, since M and N are C1 diffeomorphic, they are homeomorphic, and in particular, N is compact. That's because M is compact. And we can apply the theorem now to M because it's a C-infinity manifold. Indeed, we just need to apply the theorem for the case of C-infinity manifolds. We don't need, in order to generalize, to see, we could actually, this proof would work for every CR manifold with R finite, meaning that if you prove the result for C-infinity, you get automatically the result for every finite differentiable class, okay? So since here we apply the case that we already know, and indeed the subcase for C-infinity manifolds, and as a consequence there exists there exists an embedding from N 2R to n plus 1, where twice small n plus 1 is twice the dimension of big N plus 1. That's here the issue is that the dimension of n is equal to the dimension of big M, because these two manifolds are C1 diffeomorphic. So we have here a map that is a C infinity embedding. Now notice that the composition of psi and F is indeed a C1 map from M to R to twice small n plus 1, that since psi is a C1 diffeomorphism, we also have that the composition of psi and F is a C1 embedding. And as a consequence, we get the Whitney embedding theorem for C1 manifolds, right? So we see here that to have the possibility of considering that a CR manifold is C infinity can be very useful, okay? As it is in here, in which we are able of proving the Whitney embedding theorem for the C1 case without actually needing to change the proof. What we just need to use is that a C1 manifold is also a C infinity manifold, right? Okay, and so this technique over here, in which we can suppose in practice that every manifold is indeed C infinity, is going to be very useful from now on. We studied properties in the space of CR maps between differentiable manifolds that define open subsets, the so-called stable properties, or dense subsets. This makes clear that it is very interesting to understand the structure of the space of CR maps for either the weak or the strong topology. And indeed, that will be the subject of our next lecture. So far, we provided descriptions of these two topologies in which we used in the definitions local charts. We are going to try to remove this dependence on local charts from the definitions in next lecture. Thank you for your attention.